Okay. Okay, so thank you. It's a pleasure to be here, and I'd like to start by thanking ICTS for hosting this meeting, which has by far the widest blackboard I've ever seen. I'm almost hesitant to pollute its serenity with my mathematics, but I'd also like to thank the organizers. So, everything I'm going to tell you about today is joint work with Michael Wolf. Michael Wolf. So to start with, let me tell you about fairly old and very general construction that our work studies a specific instance of. So this will be what I call the Calabi Cheng correspondence. I guess this dates from 1975. So here, this is really a theorem of Cheng-Yao that resolves a conjecture of Calabi from the early 70s. So here's what this correspondence gives. Actually, the correspondence is more general than I'm going to write down. It applies to any dimension, but I'm going to write down the two-dimensional version of it. So suppose that we have a set omega in RP2 that's properly convex. So what properly convex means is that it is an open and bounded subset of some affine chart for RP2. So think a bounded open set in the plane that's convex, and then consider the plane as being part of RP2. If you have any such thing, and this correspondence gives you from that a pair, R and C, where R is a simply connected Riemann surface. In fact, it's more than that. It's a Riemann surface structure on omega. And C is a holomorphic cubic differential. On the Riemann surface R. Okay, and what interests me very much about this construction is that it's projectively natural. In the following sense, the group SL3R, which I'm going to think of as the projective group, the group of projective transformations of RP2, acts on RP2, and the image of any properly convex set is another properly convex set. When you act on a set by an element 3R, this construction is natural in the sense that the corresponding objects, the Riemann surface structure and the cubic differential, will be related to one another by a biholomorphic transformation between the Riemann surfaces. Okay, so it goes from a world of projective objects, fundamentally a kind of real differential geometric object, to some kind of holomorphic data. So what am I going to tell you about this correspondence other than its domain and its range? Yes, yes it is. So the only thing I want to tell you about this construction is what its intermediate objects look like. It's a construction in affine differential geometry, and it goes roughly like this. You start with a subset of RP2, and out of this, you build a surface in R3 that lives over omega, in the sense that omega is a subset of RP2, so you could think of an affine chart for that as the plane z is equal to 1. Here's omega. And S is some surface in R3 that's asymptotic to the cone over omega. That's S. And this is the surface that has a very special property. It's what's called an affine sphere. The definition of that is going to be more or less irrelevant, but later I'll give you some differential equation that will end up being equivalent to the objects that we study defining an affine sphere. So then from this, you get a few things. You get G, a Ramanujan metric, on S, which is not quite the same thing as the induced metric from R3 in the Euclidean sense. Rather, it's the induced metric in some SL3R natural sense of affine differential geometry. Probably a good way to think of G is that it's something like a rescaling of the Hessian of this surface F, a strictly convex surface, that ends up being invariant under projective transformations. You get a Riemann surface, you get a Riemannian metric, and of course, any Riemannian metric on the surface has an underlying Riemann surface structure, and that's R. The underlying Riemann surface structure of G, just meaning the Riemann surface structure in which multiplication by I is corresponds to being orthogonal and of the same length for G. So then that's G, but then separately, this surface S has a connection on its tangent bundle. That's the restriction of the flat connection of R3. Flat connection of R3. But once it has a Riemannian metric, it gets another connection on its tangent bundle, which is the one that comes from G. So now, when you have two connections on the same bundle, everyone knows what to do. You take the difference, and that's some kind of tensor. Here, this is an analog of the second fundamental form. So after raising and lowering indices, this difference gives you a cubic form on the tangent bundle. I guess at first, this difference would be something that takes two tangent vectors and gives you another one. So you use G to turn it into a cubic form on the tangent bundle of S. And then it turns out that for the special class of surfaces considered here, that cubic form is always the real part of a unique holomorphic cubic differential C. The construction looks something like this. You lift a domain in RP2 to a special surface, and you get a metric, and you get a cubic form. And those two together determine a Riemann surface structure and a holomorphic cubic differential C. Okay, so what I think is interesting about this is that you can ask the following question. If you have a favorite class of convex subsets of RP2, you could ask what the corresponding Riemann surfaces and cubic differentials are. Or if you have a favorite, more restrictive of a question at first, if you have a favorite simply connected Riemann surface and a favorite family of cubic differentials on it, you could ask whether they come from a nice convex set in RP2. So let me tell you two theorems that have the same basic flavor, which is that there are only two possibilities. Yeah, that's right. It's either the disk, it's biholomorphic to either the disk or to the complex plane. Let me tell you about two theorems that both say, once you restrict attention to a certain family of properly convex sets or a certain family of pairs RC, then this gives a bijective correspondence in which you can describe both families, both the family of convex sets and the family of cubic differentials. So I'm going to give them in reverse chronological order. So the first one comes from a previous joint project with Wolf, of which this is a continuation. This is from 2015. So we showed that under this, so maybe I'll abbreviate it CCY for Calabi, Cheng, is that this correspondence, Calabi, Cheng, gives a homeomorphism between the following spaces. Between the space CD of a polynomial of degree d times dz cubed. So that's a holomorphic cubic differential on the complex plane that happens to have the special form of being a polynomial in z times dz cubed. And I said it's a, I think I said it's a moduli space, so I want to actually quotient by a natural notion of isomorphism here, and that's going to be if two polynomial cubic differentials are related by a complex affine map, z goes to az plus b under pullback, then you declare them to be equivalent, to be the same point in this moduli space. So that's one space. It gives a map from this, and I'm going to call that map alpha, to PD plus 3. This is the space of convex polygons with D plus 3 sides or D plus 3 vertices in RP2 up to SL3R. So alpha here is an inverse to the Calabi-Cheng correspondence that I introduced before. As I stated it over there, that correspondence would take a convex set and give you a Riemann surface and a cubic differential. This says there is a corresponding inverse construction that starts with any polynomial cubic differential in the complex plane and gives you all of that intermediate data, in particular the convex set, which is actually a D plus 3 gon. So you can do a quick dimension count and check that these spaces at least have the same dimension. Here, if you're looking at n-gons, then you would have if you're looking at n-gons, then you would have 2n dimensions for the vertices, minus 8 for the action of SL3R. Here, if you're looking at polynomials of degree d, then you have d plus 1 coefficients. Each one is a complex number, and then you subtract off 4 dimensions for a and b. Okay, and I think you'll find if n is d plus 3, then these are equal. So let me give you one example of what this construction would relate. For example, if you look at the cubic differential z squared dz cubed, what could that be? Its image under alpha should be some kind of polygon with 5 vertices. It turns out it gives the equivalence class of the regular pentagon. So why does it do that? Well, let me point out that if you take a 5th root of unity, zeta, then replacing z with rotation by 1/5 of a turn of z, zeta z, this will actually leave the cubic differential z squared dz cubed invariant, because you get 2 zetas coming from the z squared and 3 coming from the dz cubed. So this is kind of the natural point in the space C2 that has 5-fold symmetry, and this is the natural point in the space of pentagon that has 5-fold symmetry. So that's an example of what this construction gives. Okay, so that's polygons. Let me tell you about an earlier theorem by due independently to Francois Labourie and John Loftin from about 2000 that studies almost the opposite extreme. So these are the simplest convex sets, which have very few symmetries. This theorem is going to be about some of the most complex convex sets that have a huge group of symmetries. This theorem is from about 2000 and due to Labourie and to Loftin independently. So this says that the Calabi-Cheng correspondence gives a, I'll say diffeomorphism between 2 moduli spaces of a similar flavor to the ones over there. So I have to start with let S be a compact surface of genus G, at least 2. And this correspondence gives a diffeomorphism between space that I'll call C of S. C of S is the total space of the bundle of holomorphic cubic differentials over the moduli space of Riemann surfaces homeomorphic to S. So here M of S is the moduli space by holomorphism equivalence classes of Riemann surfaces of type S. And here C is the bundle of holomorphic cubic differentials. Okay, so in total, C of S is the space of all pairs. Riemann surface structure on S and cubic differential on that Riemann surface. It gives a map from those to I would call P of S, and this is going to be the moduli space of convex RP2 structures on S. Let me take a self-serving definition of convex RP2 structure. It will be when you have a convex open set, properly convex open set omega inside of RP2, such that there exists a group gamma inside of SL3R that first of all, thought of as a group of projective transformations, leaves omega invariant, and secondly, where the quotient is diffeomorphic to S. So this means that omega is a complex set with a huge group of symmetries under the projective group. It has a whole surface group's worth, and this is what a convex RP2 structure on S means. There's also a local definition by charts in which this thing would become the image of the developing map. So the way you would go from this to a holomorphic cubic differential is, I think, pretty clear. You would start with omega and apply Calabi Cheng, and then you would get a pair of a Riemann surface, which I'm now going to call R tilde, and a cubic differential that I'll call C tilde. Because omega carries this big group action, and because the Calabi Cheng correspondence is natural for the projective group, these R tilde and C tilde both carry an action of the same group gamma. But now it's an action by biholomorphic maps. You can consider the quotient objects R, which will be R tilde mod gamma, and C, which will be C tilde mod gamma. And that will be a point in C of S. It's a pair of a Riemann surface and a holomorphic cubic differential. Okay, so in both cases, I've stated the theorem as the existence of a map inverse to this affine sphere construction. All right, so now I've told you about two theorems. The main theorem in the work that I'm talking about today gives a kind of glue between these two results. It says you can obtain these polygonal examples as limits of the compact surface cases. Let me start talking about the main theorem. So we study a specific type of divergent sequence in this space of holomorphic cubic differentials on a compact surface. So let S be as before. Compact surface of genus at least 2. Now, let Rn and Cn be a sequence in that space of holomorphic cubic differentials on S with the following property. I want the Riemann surfaces to remain in a bounded set of the moduli space, but I want the cubic differentials to go to infinity. So the entire sequence Rn is contained in some K, which is a compact set inside of the moduli space. And then something that I can make sense of only because I've had this assumption of boundedness of Rn, I want the cubic differentials to go to infinity. So let me just say briefly what this means. Maybe, no, I won't draw a picture. Over a compact set in moduli space, you choose any, say, norm on the vector bundle of cubic differentials that you want. Because we're dealing with a compact set, it won't matter which norm, any two will be equivalent. Then what I mean is I want the norms of the cubic differentials to go to infinity. So this is some kind of vertical divergence in this bundle that you're going to infinity in the fiber direction while staying bounded in the moduli space direction, as opposed to another type of degeneration you could consider where the Riemann surface goes to infinity and maybe the cubic differential remains bounded. Okay, so that's our case of interest. Okay, so then we have a subsequential theorem about what happens to the corresponding convex sets in RP2. Our theorem is about the behavior near a point, so let Pn be a sequence of points in Rn, a sequence of base points. Then, after passing to a subsequence, we have the following. The associated convex sets in RP2, coming from these pairs Rn, Cn, actually converge to a convex polygon, and you can predict which polygon it's going to be. It's the one that you get from a specific polynomial that you can extract just by looking at Cn in the neighborhood of Pn. So now I'll write that. So then, another piece of chalk. After passing to a subsequence, I'll call it omega n and maybe Pn tilde. So here omega n is the subset of RP2 associated to Rn Cn by Calabi, Cheng. Pn is some point in omega n that corresponds to Pn. I say that because omega n is the universal cover of Rn, but realized inside of RP2 in some specific way. So what I mean is pick any lift of the point Pn, which lives in the surface S, to its universal cover. Let that be Pn tilde. And these converge in a topology that I'll tell you about in a moment to a specific polygon, alpha of chi and some point P, where chi is a monic polynomial that I will call the local limit as n goes to infinity of the sequence of cubic differentials Cn about the base points Pn. This alpha here is the map from the previous theorem. The thing where you give it a polynomial and it constructs a polygon. So now what I have to do is tell you what this local limit thing is about. So that's going to be an important part of the whole construction. Before doing that, let me tell you what this arrow means. Can I go all the way to the right here? Or should I stop at some point and continue? Okay. I won't go to the boundary. I'll remain in a compact subset of the board. Okay, so what topology do we put on these? So here, to say that a sequence of convex sets with base points, we're going to call them Qn, converges to omega Q. This means following things. It means up to the action of SL3R. And in the Hausdorff topology. So it means there exists a sequence AN in SL3R such that if you look at the closures of omega n, so then those are closed subsets of the compact space RP2, the kind of thing that the Hausdorff topology applies basically to, then their images under these projective transformations AN converge in the Hausdorff sense to closure of omega, and AN QN converges to Q, and Q is actually an interior point of omega bar. It's not in the boundary. Okay, so this notion of convergence might look a little strange, but it's the best you can do when the construction is in SL3R natural 1. I mean, it doesn't actually give you a uniquely determined set in RP2. It gives you one uniquely determined up to the action of SL3R. this is the best you could hope for. But note that this kind of convergence, this topology, can have interesting behavior even if the sequence omega n is constant. Say, even if omega n is equal to omega for all n. So I'll just sketch what a picture of that might look like. You could start with a sequence that looks like this, an ice cream cone domain. Supposed to be convex. There's a sharp point. So this is omega 0. And a sequence of points, I guess I was calling them Q, Q1, Q2, and so on, that converges to that point. Okay, so what could we say about the behavior of this sequence omega 0 with base point Qm? Well, leaving it alone is not going to do because the sequence converges to a boundary point. And I've required in my notion of convergence that at least after applying some projective transformations, that the base points actually converge to an interior point. But we can fix it. We have this giant non-compact group, SL3R, that we can act by. So in this case, something that you could do is use maybe an element of SL3R that has some expanding behavior around this point, and maybe contracting behavior around these points, and preserves this triangle, to turn this, after applying AN, into something that looks more like this. And close to a triangle, with the base point right in the middle. So then the sequence after transforming might look something like this. You could have a limit that is a triangle with some interior point. Okay, so fixed domain with sequence going to the boundary becomes varying domain with a point that more or less doesn't move. It stays in the interior the whole time. So that kind of thing could happen. One of the reasons I write that on the board is to convince you that it wouldn't be all that surprising to get a polygonal set as a result of taking a limit of some general convex open set. Okay, so I did one of the two things I promised. I told you about the top arrow. Now let me tell you about this local limit construction. What is it? The local limit as n goes to infinity of a sequence, Riemann surface, cubic differential, and base point, which is calling the Pn. This is a polynomial cubic differential on C. And it has the following properties. Property 0 is that it almost exists. It is almost well defined. So the construction doesn't quite give you a completely natural polynomial cubic differential. It gives you one that is well defined up to acting by the affine group, Az plus B. When I took the output of this procedure and fed it into that map alpha that I defined before, that's exactly the kind of thing that you can do when you know a cubic differential up to the action of the automorphism group. Okay, property one is that it's truly local around the point, around the sequence of base points Pn. In other words, this local limit is uniquely determined by the restriction of Cn to a neighborhood of the point Pn. Well, okay. Let me say this. Suppose that Pn converges to a point P. Because the Pn's live in a compact surface, after passing to a subsequence, you can always arrange that. So then what I want to say is, it's uniquely determined by the sequence of restrictions of Cn to a neighborhood of the limit point P. It really focuses on what is happening in this cubic differential Cn near the base point Pn. It's local. And now let me tell you what it gives you in one special case. So suppose that Cn is actually just a sequence of multiples of a fixed cubic differential, we call it C hat. Where Rn goes to infinity as n goes to infinity. So then, I can tell you exactly what the local limit is. Well, at least in one case. So for the simplicity of the rest of this lecture, from now on, I'm going to replace the completely general case of varying Riemann surface, varying cubic differential, and varying point with the following special case where all of the genuine complications can still be seen. Fixed Riemann surface, varying cubic differential, fixed base point. Okay, so from now on, the base point's fixed, Riemann surface is fixed, and you're varying the cubic differential. So then a further special case is where the cubic differential is only varying in an uninteresting way. You're multiplying a fixed one by a constant, Rn. Well, then the local limit, as n goes to infinity, of this Cn is just z to the d dz cubed, where d is the order of vanishing of the limit cubic differential C hat, in the projective sense, at P. All right, so let me just decorate this with a little bit of extra terminology. So this sequence of cubic differentials doesn't have any limit, right? It goes to infinity. It looks like larger and larger multiples of the fixed one. But it does have a projective limit. If you're allowing yourself to multiply by a constant in order to arrange convergence, then you could just multiply by 1 over Rn. And then C hat would be your limit. So I would call C hat the projective limit of the sequence of cubic differentials. And in this ray case, the local limit is just going to describe what that projective limit looks like near P. It's going to be z to the d dz cubed, the canonical local form for a holomorphic tensor. So it always looks like z to some power times dz to the appropriate degree. Okay, so that's what you get in the ray case. What do you get in general? The third property before I tell you the construction is the following degree bound. In general, we can always do the following. We can take our sequence of cubic differentials, Cn, and say, up to rescaling them by positive real scalars, we can always arrange for them to converge to some point, just like here. But it may not be that the sequence is constant after the rescaling. So Cn can be written as some constant, Rn, times Cn hat, where Cn hat converges to C hat as n goes to infinity. So if you put a norm on the space of cubic differentials, all I'm saying here is let Cn hat be the unit norm cubic differential that is a multiple of Cn. Then you can always pass to a subsequence so that those unit norm ones converge to some point C hat in the unit sphere. So this is kind of the general picture. So then there's a number that we can associate to this sequence, which is what is the order of vanishing of C hat at the point P. So this I would call the projective degree. Or more pedestrian term for it would be the number of colliding zeros. I'll draw a picture to suggest where that term might come from, but here's the general case. The order of vanishing of the projective limit is just an upper bound for the degree of the local limit. Yeah, why don't I start calling it the local limit of Cn? Because it's implicit, we've fixed R and P for now. Okay, and this is what I would call the local degree. Just to make a quick picture of what I mean by colliding zeros. We're working on a compact Riemann surface. A cubic differential is uniquely determined up to a complex scalar just by looking at where its zeros are, if you know them up to multiplicity. So Cn looks something like this. It has a scattering of a certain number of zeros. Probably know by heart what that number is in terms of G, but some number of zeros. And as n goes to infinity, these zeros move around the surface. And maybe some of them come together as n goes to infinity. Then we would have a projective limit, C hat, that has maybe a 0 of multiplicity 3 and another one over here of multiplicity 4. So this is a picture of the projective degree. And what's going to happen is that this local limit will factor in some of the zeros of the sequence Cn, but not necessarily all of them. It's a way of deciding which of the family of zeros that converge to a given point are converging fast enough to be relevant to the limit convex set and which ones don't matter. Right, so that's the next point, is constructing the local limit. So I'll tell you about that now. Yes, yeah, absolutely. Like in the ray case, for almost all points in the surface, you just get dz cubed. If C hat is not 0 at the point, then you just get dz cubed. But then for selected points where C hat actually vanishes, you can get something more interesting. But you only ever get z to the d from the ray situation. In general, though, you're going to get some polynomial in which its zeros reflect the limiting way in which the zeros of Cn come together at the point. I'll explain that. So construction of the local limit. Well, let me tell you in the ray case first, where it's going to recover this claim that I made before, that it's just z to the d dz cubed. Here's the idea. So recall we're in the ray case, so Cn is some multiple Rn of C hat. And we have a base point P that we fixed. So something you can always do is write C hat as z to the d dz cubed in some neighborhood of P with respect to a local coordinate z, where in that coordinate P corresponds to the origin. Okay, so you can always do that. Just express C locally in a coordinate adapted to its order of vanishing at the point. But that's for C hat. So then what does C look like? Well, let me note that this is on some set that we can think of as a small disk centered at 0 in the plane with coordinates. Now here's the idea. Cn itself can now be expressed in that same local coordinate system as Rn times z to the d times dz cubed. This has no limit, right? Rn is going to infinity. The idea will be to instead apply some dilation to the coordinate system to ensure convergence. So let's consider a new coordinate related to this one by a dilation. So it's going to be W is lambda n times z, where lambda n is some positive real scale factor. let's consider, what does Cn look like when written in the W plane, when written with respect to coordinate W? So notice that the first expression in terms of Z, this holds on the little disk, whereas this next expression is going to hold on absolute W less than or equal to lambda n times epsilon. So if lambda n is very large, this is going to be an expression for Cn on a very large disk. So let's just write it. Cn is then Rn times Z is lambda n inverse W, and dz is lambda n inverse times dw. So at the end, you just get Rn times lambda n to the negative d plus 3. Oops, I forgot it. Added d. W to the d, dw cubed. And this is going to tell us what scale factor we should use. If we let lambda n be the positive real number so that that to the negative d plus 3 is equal to Rn, then let's now choose lambda n to be Rn, 1 over d plus 3. Then what we get is Cn is exactly W to the d dw cubed on absolute W less than lambda n epsilon. So let me make a picture of what we've just done. Holomorphic differentials are kind of like measures, right? I mean, if this were a quadratic differential instead of a cubic differential, dz squared is the kind of thing where if you take the absolute value of it, that's a measure. So I think of a holomorphic differential as being like a mass distribution. Maybe you have to take some power of it for that to literally be true, but the intuition is right. So what Cn looks like is this. It is a huge amount of mass concentrated in a tiny disk of radius epsilon. Huge because Rn is large. What we've done here is we've applied a dilation to the coordinate system in which a huge amount of mass in an epsilon ball becomes a totally reasonable amount of mass in a lambda n epsilon ball. After the fact, though, we now have locally uniform convergence of this to the differential W to the d dw cubed. Let me write it, and then it's going to look very strange, and let me convince you it's true. This converges locally on C to W to the d dw cubed. Why does this look very strange? This looks like the constant sequence, right? W to the d dw cubed each time. But for any given value of n, the thing in the box here is only defined on some disk. The thing on the right is actually an entire cubic differential, right? This is on C. But as n goes to infinity, lambda n goes to infinity, and it eventually engulfs the entire plane. So that's the sense in which we have locally uniform convergence. All right, so all the same features are going to come up in the general case. It's just going to be a little harder to select the scale factors. Let me explain that now. So what can we say now? Well, of course, we can write Cn is a scale factor times something that converges. This is where Cn hat goes to C hat as n goes to infinity. And now we can, as before, use a coordinate z that's adapted to the projective limit C hat. So use z in which C hat is locally expressed as C to the d dz cubed. And here's what can we say then about Cn. Then, in that same coordinate system, Cn is a large scalar times something that looks like a small holomorphic perturbation of z to the d. So that would be, it has a bunch of zeros near the origin. So product from I equals 1 to d of z minus the ith 0, zn superscript I. Okay, so that accounts for the zeros near the origin, times some holomorphic function. It doesn't have any zeros, qn of z, all times dz cubed. this is where Qn of z converges to 1 locally uniformly in absolute z less than epsilon. Okay, so that's end. For each I, Zn converges to 0 as n goes to infinity. So what we see when we back off from n equals infinity, and you just have z to the d, and you back up to some finite n, now the zeros, there are d of them. They're all near the origin, but not exactly at the origin. And then there's also some maybe quotient holomorphic function Qn of z that you can't control so much. That's what Cn looks like. Let's apply the same dilation trick. Let's apply dilation where W is lambda n times z. So the first thing we could do is try what worked last time. So let's just write Cn as Rn times the product m equals 1 to d of z, which is now lambda n inverse W minus Zni, times Qn of z, which is lambda n inverse W, times dz cubed, which is lambda n to the minus 3 dw cubed. So in this language, what we did last time was we then factored out this lambda n inverse from all d of the terms in order to get a big lambda n to the d plus 3. So we could try that here. This is equal to Rn times lambda n to the negative d plus 3. And now this product becomes product from I equals 1 to d of W minus a huge constant multiplied by a tiny complex number. Okay, and then multiplied by Qn of lambda n inverse W, W cubed. So how does this look? Ideally, what we would want is for this factor in the middle, which is a polynomial of degree d, to actually converge as n goes to infinity. Then we would recover the previous situation if we just arranged for this leading coefficient to be 1 by choosing lambda n appropriately. Notice that since Qn verges uniformly to 1, the same thing is true for Qn of lambda n inverse W. So this part goes to 1. But here's the problem. Once you choose your scale factors lambda n so that Rn lambda n to the negative d plus 3 is 1, you then have no choice about what happens to these factors inside the polynomial. Lambda n times Zni is the product of a large scale factor with something very close to 0. And you don't know who wins. Maybe lambda n is going to be growing so quickly that it blows all of the zeros up way far from the origin. Or maybe even after the scaling, all the Zn's go to 0. Or maybe something in between. But in the case where some of them go to infinity, that's a serious problem, because then this expression does not have a locally uniform limit in the complex plane. So let me tell you what fixes that. You have to choose to distinguish between near and far zeros. Okay, so let's select some number k between 0 and d. And then let's do the same kind of factoring out, but let's only apply it to the first k terms. Oh, let's also pass to a subsequence, not a subsequence. Let's number the zeros. So that they come in increasing order of absolute value. Zn1 has absolute value less than or equal to Zn2, and so on. So of the d zeros that are all coming in toward the origin, you just number them in weakly increasing order of absolute value. Let's do that. And then let's select that we're going to say the first k of these are going to be the ones that we think of as being near the origin. We want to preserve them to appear in this limit polynomial. And then the others we're going to think of as too far away to matter. Let me show how that's reflected in writing the cubic differential. Then Cn can be written as Rn times the product of these first k factors. So in these first k, I am going to factor out the lambda and the inverse. W minus lambda n dni. Then we get a lambda n to the negative k up front. But then for the other d minus k terms, I'm going to leave the lambda inside. This is from I equals k plus 1 d of lambda n inverse w minus dni. Okay, and then we have an additional 3 factors of lambda n inverse, negative k plus 3 dw. And my q, yeah. Qn lambda n inverse dw cubed. So what would we want for this expression to converge nicely? What we'd want is for this part to converge to some monic polynomial of degree k. And for the rest of it, which I'll put a yellow box around, should just be bounded away from 0 or infinity. Let's say, in fact, why don't we try to make the rest of it just equal to 1? How would we do that? The idea of selecting near and far zeros should be the near ones are the ones that lambda n Zni converges to some point in the complex plane after passing to a subsequence, but that lambda n times Zni goes to infinity if I is greater than k. So these are the far zeros. If that is true, if lambda n Zni goes to infinity, then this difference here is the difference between two things that are of entirely different scales. Lambda n inverse w is something much closer to 0 than Zni is. So this is then going to be approximately equal to, in absolute value, just Zni. So this suggests a value that you should use for the scale factor. So what should it be? It suggests you should pick your lambda n so that lambda n to the k plus 3 is equal to Rn times the product of all the far zeros. Write that formula. I equals k plus 1 to d of absolute Zni. The overall coefficient times the norms of the far zeros to the 1 over k plus 3. Okay, but this is a little bit puzzling because to figure out which scale factors to use, we had to decide how many of the zeros are going to be regarded as near the origin and how many are far. The following lemma says that you don't actually have any choice in that matter. It is forced by the sequence. Here's the lemma. Once we pass to a subsequence, so that the zeros are numbered in, once we've numbered the zeros in increasing order of absolute value, then there exists a unique k, could be 0, could be d, such that if we define lambda n by the formula at left, just wrote it. Let me not write it again. Let me just call this star. Then the far ones go to infinity and the near ones have limits. So the lim sup as n goes to infinity of lambda n times the norm of the ith zero is less than infinity if and only if I is less than or equal to k. I should also say that lambda n still goes to infinity. That's essential. Okay, so what does this mean? It means that there is a correct number to choose, a correct number k, so that if you rescale it so that those k have limits, then all the rest go off to infinity, and then you have a monic polynomial limit. So then I can tell you what the local limit is. We pass to a subsequence so that all the near zeros converge. After the rescaling, lambda n times zn I converges to some point that I will call wi as n goes to infinity for I less than or equal to k for the near zeros. Then the local limit of this sequence RCNP is just the product of w minus wi from I equals 1 to k, dw cubed. So that's a simple definition, but choosing the k was the important part. And now what we've achieved is that this polynomial is the locally uniform limit of these cubic differentials Cn in the W plane. Okay, so that's how you choose the limit. If you have this scale factor, some of the zeros disappear. They don't contribute to the degree. The ones that do remain bounded, even after the deflation, there are k of them, and you get a polynomial of degree k. So I think I have 10 minutes to tell you how this all fits into the rest of the proof. So that was all defining the local limit, one of the terms that appeared in the statement of the main theorem. Yeah, for example, if you choose a point where the projective limit of the CNs doesn't vanish, then you'll just get dw cubed. You could even choose a point where the projective limit has a high order zero, but maybe they're all far zeros, and you could still get dw cubed. Maybe I should have said this, but the fact that I keep saying you often get dw cubed as the limit means most of these limits of these convex sets are just triangles. Alpha of dw cubed is the triangle. The generic situation is that these convex sets converge to a triangle unless you happen to choose the base points very carefully to track the movement of multiple zeros of C, in which case you might see a quadrilateral or convex set. Goes to 1. So that's the part in yellow here. You have to use that specific product to the 1 over k plus 3 in order for the stuff in yellow to converge to 1. Or really to have, you have to use something equivalent to that by a uniform constant in order for the stuff in yellow to be bounded away from 0 and infinity. So you could arrange for scale factors to have any number of the zeros converge, but then either you'd have overall mass accumulation for the cubic differentials, and an infinite amount of mass would be piling up near 0, or you'd have mass diffusion, where the lambda n's are too big, and all the mass disappears to infinity. There's a unique k such that these two things are tuned to work together, that the mass distribution converges to one given by a polynomial. Okay, so now let me tell you, how does all this stuff about cubic differentials actually turn into a theorem? Let me give you an outline of the proof. The whole thing is about reconstructing, key point is reconstruction of the Riemannian metric G that appeared in that affine sphere data from the pair R. So going from a Riemann surface and a cubic differential to a Riemannian metric G such that the rest of the construction gives you an affine sphere, this is an instance of solving a differential equation that is either called the Wang equation in the affine spheres literature, but it's also an instance of the self-duality equations in the sense of Hitchin for a certain rank 3 Higgs bundle. So let me tell you what that equation becomes in this case. It's, I think, just a beautifully simple equation. You're looking for a Riemannian metric G so that the Gaussian curvature of it is -1 plus a small correction. But the correction is related to the cubic differential. It's the pointwise norm of the cubic differential squared relative to G. So let me say what this means here. I'm saying that if you start with a Riemann surface and a cubic differential, and you find a Riemannian metric G that solves this equation, then that can be put into the rest of the affine spheres machinery to give you the surface in R3, to give you the convex set in RP2. You can go from there. But this first step of actually finding the metric G is an important one. And in our case, we want to estimate the asymptotic behavior of G as n goes to infinity. So here's what we actually want to know. Let me just note about this equation that if C is 0, then if G is the Poincare metric, a hyperbolic metric on the surface, that's a solution. On the other hand, if you don't care about the fact that it is singular at the zeros of C, if we take G to be the cubic differential to the power 2/3, is a singular flat metric on the surface. It's analogous to a cubic differential metric. No, it is a cubic differential metric. It's analogous to a quadratic differential metric in that it has cone singularities at the zeros of C, but this 2/3 is arranged so that it looks like a bunch of 1/3 of planes put together instead of half planes. So this metric is a solution of the self-duality equation away from the zeros of C. So the general picture is that the actual solution to this is going to be a smooth Riemannian metric that interpolates between these two possibilities. Near the zeros of C, it's going to look kind of like the hyperbolic metric. Far from the zeros, it's going to look kind of like the cubic differential metric. So the actual solution smoothly interpolates between these. So what does our proof look like? It's not hard to show that if you have C2 convergence of the Riemannian metrics, this implies Hausdorff convergence of the associated convex. So what we actually need to do, okay, first of all, some general elliptic theory, so that if you have uniform convergence of the metrics, then you can elevate that to C2 convergence using the equation. So then what we need are some kind of uniform estimates for G. Let me draw a picture of what those look like, and then I'll be done. So here's our compact surface. And we have some zeros of the cubic differential. And we have some metric G, which I'm going to draw as if it's a graph over the surface of a function. One way to make that precise is you could think of G as being a pointwise multiple of the hyperbolic metric and then graph that function. So its general behavior is that it's going to be huge almost everywhere, but then it's going to kind of dip down near the zeros of the cubic differential. So this is a picture of the Riemannian metric Gn corresponding to cubic differential Cn. And what we've done in this local limit construction, we've selected a small neighborhood of one of the zeros, and we've expanded it to a giant disk in the W plane. Maybe I should draw that there's a cluster of several zeros here. So those are all very close to the point. When you apply this dilation machinery, then you get some zeros that have some kind of limiting configuration, k of them. We have two different metrics we can look at here. We could look at Gn pulled back to the W plane, or we could look at G that comes from the limit polynomial chi. So here, recall that chi was my name for the local limit of the cubic differential Cn. So we have two different metrics on some disk in the plane, some big disk in the W plane. One of them is where you take a metric on this compact surface that is huge almost everywhere, you restrict it to a small disk, and then you blow that small disk up to a big disk in the plane. The other one is where you solve an equation on the entire complex plane using that theorem that I stated about polynomial cubic differentials to get a metric on all of C. And you want to compare these two. So what we show is that while the cubic differential metric, which actually has zeros, is not a very good model for the metric Gn, at least near the zeros, that there is a specific smoothing of it that we can construct by hand. It has two properties simultaneously. First of all, that it gives an upper bound for the metric Gn, so it should actually be above Gn. Right? Specific smoothing lies above Gn. And then when you transport it to the W plane, it actually remains bounded. What that allows you to do is to apply an Arzela-Ascoli argument, to say that you have a sequence of metrics on disks that eventually exhaust the plane, and they're all bounded when you restrict to any fixed radius. So you can then check that the equation implies equicontinuity of that sequence, so that you have some kind of limit, and then our uniqueness theorem for these metrics that come from monic polynomials will imply that the limit has to be exactly the polynomial, exactly the metric that comes from the polynomial by that construction also. So this gives C0 convergence of the metrics. And then, as I said, you use a little bit of elliptic machinery to turn that into C2, which implies Hausdorff convergence of the convex sets. I think I'm out of time. Thank you.
I think you still have 5 minutes. You still have 5 minutes. If you still have 5 minutes, if you want.
Still have 5 minutes.
Yeah, yeah.
Oh, okay.
But yeah, if you want to say something.
Any questions?
Yeah. Any questions?
I'll be happy to give an answer.
Mahan Maharaj has a question. Mike.
The local degree at a point blows up. Are you converging to zero, the zero cubic differential? I mean, so just take something like that. Looks like z power n dz cubed.
Could you say, what do you mean by local degree blows up?
So if you take a cubic differential which locally looks like z power n, I mean, so that's your. If the degree does not remain bounded, is that possible?
Oh, I see. Okay. The theorem is about a fixed genus. So it's a sequence of cubic differentials where the total number of zeros is bounded independently of n. I mean, I wouldn't rule out that you could say something in that case. But at various points, we do appeal to the uniform bound on the degree in this construction.
So is there an analogous result in the simpler setting of quadratic differentials and hyperpolygons? Do you get ideal polygons or something?
Right. So this was about comparing cubic differentials on compact surfaces to polynomial cubic differentials on the complex plane. There's an analogous picture where you would say, look at polynomial times dz squared. And the analogous object is, instead of an affine sphere in R3, is going to be a harmonic map from the complex plane into the hyperbolic plane with a polynomial Hopf differential. So it is a theorem of Freiberg's Mahan from the 90s, I think, that in this case, the image is an ideal polygon. And though they don't phrase it this way, I believe it follows from their work that this gives a map from the moduli space of polynomial quadratic differentials to the space of ideal polygons up to isometries of H2 that is surjective and that has fibers you can understand. In this case, though, you lose some information. It basically only remembers the horizontal foliation of the quadratic differential and ignores the vertical foliation. So it's not the corresponding statement is not that it's a homomorph. But okay, so having made that setup, I think your question would be, tell me if this is your question, if you have a sequence of quadratic differentials on a compact surface, can you, by an analogous procedure, extract a local limit polynomial? And then can you say that some kind of limit of harmonic maps with those Hopf differentials gives a harmonic map from C into H2 that has this ideal polygon structure? And the answer is, I think so. We don't do that. We limit our consideration to the cubic differential case. But really what this is all about behind the scenes is it's estimating solutions to the self-duality equations for cyclic Higgs bundles of any rank. So this local limit construction would work for holomorphic differentials dz to the n, or for any n. We give you a limit, and similarly, this super solution machinery that I sketched here with a bit of an estimate for the Ramanujan metric, that would also work. But the end game of the argument, where you pull it all back to affine spheres and Hausdorff convergence of sets in RB2, we only do that part for cubic differentials.
Okay, so any more question? Yeah.
So the thing is, so the issue is a whole bunch of zeros are coming together and bunching up, right?
Yeah.
So and then the way you deal with it is you lose a lot of information. I mean, it's possible that the two pairs of zeros come together at some faster speed, and then the pair come together like at a small speed. So I mean, these polynomials come like a pattern of the zeros somehow, right? But maybe I want to keep track of the sub-patterns of the big pattern. Is there a natural way to do that? I mean, especially for...
So not only is there, but we have to do it in the argument, in the part of this that I've carefully suppressed from discussion. So here's what you really have to do, in brief. This whole construction was about the local limit at a point P, and it gave you a sequence of scale factors at P, and a set of near zeros at P, and a set of far zeros at P. You could redo this for any base point P whatsoever. But if you look at all possible choices for P, you only really get D different answers. You can reduce to the case where the base point that you've marked is one of the zeros. So then every zero of the polynomial has a cluster of near zeros that kind of remain bounded as you go to infinity, and then the rest are far zeros. So those clusters can have different sizes, and each cluster has its own scale factor lambda. It turns out that in going from the cubic differential metric to some smoothing of it to estimate this metric Gn, the amount of smoothing that you have to do is not governed by any single scale factor that's universal to the sequence. The amount of smoothing you have to do is the local scale at the zero that you're smoothing. So all of those, every single cluster comes into this Ramanujan metric estimate, not just the one that I used to introduce the idea of a local limit.
So is it possible to keep track of all this information and give a compactification of the space of all like quadratic or cubic differentials?
One would hope, yeah. So here is one statement that I think is true, that I will just say as a conjecture that is almost certainly true, but we don't have a proof of it written down, would be that this cubic differential that you get, this local limit, if you take its absolute value to the 2/3, that's going to be an asymptotic cone. of the sequence R with absolute Cn to the 2. So what this is really doing is constructing a base point asymptotic cone for the sequence of metric spaces surfaced with flat metric. So one thing you could do is you could look at the kind of spectrum of all the asymptotic cones of this sequence of metric spaces with diameter going to infinity. It seems like there probably is something there where you could construct a whole compactification of this space of cyclic Higgs bundles, but I don't think that has been fully worked out in any example where you have colliding zeros, which is the case that we consider here. So I would definitely see this as a first step toward something like that.
So just a silly question. If a zero is a near zero for somebody else, is the somebody else a near zero for the first one?
Yes, is it an equivalence relation?
Right, okay.
Yes.
So they really come in clusters rather than relative clusters.
Yeah, it is an equivalence relation. It's in the way, the approach that I've sketched here is surprisingly annoying to prove that. It's a bunch of calculations. But I think pursuing this asymptotic cone approach would make that easier to see. The equivalence relation would be, is the cubic differential distance between the two zeros bounded as n goes to infinity or not? And that's an evidently symmetric relation. But we have a proof that it's symmetric that doesn't depend on this.
Yeah. So any more question? Okay, if not, let's thank the speaker and